In the last section, we looked at writing some functions as a series, and we saw a lot of geometric type series in that section. In this section, we want to go a little bit more general, and we have suppose we have an f of x, and it is written in this form c0, c1, c2, c3, and so on. Notice we have x minus a bunch of x minus a's, so this is the power series centered at a, and we want to try to find the c0, c1, c2, c coefficients for a this power series. So if we were to take the derivative and differentiate term by term, actually let me start before that. If we were to try to find the value for c0, if we let x equal a, then we have c0 plus c1 times a minus a plus a bunch of these a minus a's. So all of this over here is going to go to 0. So what that's saying is our first coefficient, c0, is f at a. Okay, now if we take the derivative and differentiate term by term, the constant c0 is going to go to 0. Then we have c1 plus, now we're doing power rule, chain rule here, 2 c2 x minus a to the 1 less power plus 3 c3 x minus a to the 1 less power, and so on. Now if we try to find c1 the same way we tried to find c0, that is, evaluate at a, all of these terms are going to go to 0, and f prime at a is c1. So we found two coefficients so far. We found the c0 and the c1. We can do this again and find the second derivative as a function of x. So this time c1 goes to 0, and now I have 2 c2 times 1 plus 3 times 2 c3 x minus a to the first plus, if I had kept going, it would be 4 times 3 c4 x minus a squared, but I'm not going to write it out. You get the idea. So now if I want to find the coefficient for c2, we can evaluate this at a to have all of those go to 0, and we have 2 c2. Well, what I want is I want to know what c2 is, so we have f double prime of a divided by 2 is equal to c2. It would be nice if we could find a pattern and just look at this in general. So what is the nth derivative of this thing? Well, the nth derivative is going to come from that nth, this first coefficient is going to be from that nth term. So we're going to have something like 2 times 3 times, well, maybe we would rather write it the other direction. N times n minus 1 times n minus 2 dot 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 3, 2, 1 3, 2, 1 times c sub n. Okay, then you're going to have the n plus 1 times n minus times n times dot dot dot, but this is going to have an x minus a term in it plus some more stuff there. And when we evaluate this at a, we have the nth derivative at a. Now we've seen this before, that we call n factorial. So if we want to solve for the c sub n coefficient, we have the nth derivative at a divided by n factorial is equal to c sub n. So that's going to give us the coefficients of this thing that we started with. So what that means is the following. If f has a power series representation or expansion at a, then the coefficients are given by c sub n is the nth derivative at a divided by n factorial. So we can write f of x is equal to f of a plus f prime of a divided by 1 factorial plus f double prime, oops, I forgot something here, got my x minus a there, plus f double prime of a x minus a over 2 factorial, and so on. Or we can write it like this. F of x can be written as the sum from 0 to infinity of the nth derivative at a x minus a to the nth power over n factorial. So this right here is called the Taylor series of the function at a. And that's what we're trying to find for some functions in this section. If we want to have this function centered at 0, then we could have the a equals 0, and we get a more specific case, the nth derivative at 0, and so this is just going to be x minus 0 to the nth power over n factorial. This is called the Maclaurin series. So this is Taylor. It's centered at a, and then here's Maclaurin, and it is centered at 0. So we're going to see how we can write functions in this form.